impulse, isn't it?
Yeah.
Okay, so we're going to have a look at some exam questions on this particular one. I think this is probably one of the more challenging questions. It's 11 marks. I'm sure you've probably got loads of these marks already. A small smooth ball of mass m is falling vertically when it strikes a fixed smooth plane which is inclined to the horizontal at an angle alpha where alpha is between 0 and 45 degrees. So I'm just going to actually draw that beginning stage of it. So we've got a plane like this. It is falling vertically like this, and then we know it's going to bounce off in some other direction afterwards. Okay, so there it is falling vertically. Immediately before striking the plane, the ball has speed u. What are we looking for here? Immediately after striking the plane, the ball moves in a direction which makes an angle of 45 degrees with the plane. So this is 45, and it's moving off like this. The coefficient of restitution between the ball and the plane is e. Find, in terms of m, u, and e, the magnitude of the impulse of the plane on the ball. So I'm not really sure how I'm going to get to that impulse, but I think I just need to actually do the question and figure out all of these things that are going on here. So if this angle is alpha, are we able to work out what this angle here is, or this angle here is?
That angle, the top angle.
The top angle here
That's alpha.
is alpha, isn't it? Because you can imagine drawing in a line here, you know, this would be 90 minus alpha, blah, 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 and you can figure it all out. So this one running along here is u cos alpha, and this one is u sine alpha. Now we know in this new part of the diagram, it's still going to be running along here will be u sine alpha, and along the side bit is going to be e u cos alpha. Okay, but now that we know that, now that we've come up with this construction that we've got here, for this triangle that we've just got, they have told us that it is 45 degrees, and we know that u sine alpha and e u cos alpha, we know something special about those two things. They're equal to each other because it is an isosceles triangle that we've got here. This side and this side are equal because they told us it's bouncing off at 45 degrees. You could either say they're equal, or you could say that the tan of 45 is EU cos alpha over U sine alpha. So we now get that EU cos alpha is equal to U sine alpha. Cancel the U's, divide by cos, and you get that E is equal to tan alpha. Okay? We're now going to try and work out what the impulse is, and we know that the impulse, we're talking about the ones that are in this direction and this direction, because obviously there's no impulse that changes these ones that we've got here. So the impulse is mv minus u, and we're looking at the impulse as being, what does it want? The magnitude of the impulse of the plane on the ball. So we're talking about impulses going in this direction that we've got here. So that's our positive direction. So the impulse is m. Well, v is EU cos alpha, and minus u cos alpha. So we get that the impulse is m EU cos alpha plus u cos alpha. We're also going to need to use this fact that we've got here. So we get I equals m. I can also factor out the u and the cos alpha, and I just get e plus 1. And it wants it all to be in terms of m, u, and e. So which is the thing I need to be getting rid of? I cannot have this cos alpha. This thing here is the thing that is the problem. So I need to think, how can I get cos alpha in terms of e?
You take over that. No,
Tan
then you
squared
left
is
the
sec
sign.
squared.
Good, so we're actually going to have to come back to this thing that I've got here, and we're going to do a bit of manipulation. So we know that e squared is tan squared alpha. So e squared plus 1 is tan squared alpha plus 1. So 1 plus e squared is sec squared, thank you. So 1 over 1 plus e squared is cos squared alpha. But we want what cos alpha is, which is the square root of that. Well, the square root of 1 is 1, and you've got the square root of 1 plus e squared, like this. So you then just sub that back in, and we can say that the impulse is mu e plus 1, mu e plus 1, all over the square root of 1 plus e squared, which I hope is what the answer was.
I just read the question wrong, so I didn't.
Yeah, so, I mean, I got to this stage here, and I was like, oh my gosh, which is the thing? Am I going to try and change this? Just remind yourself what the question is talking about, and it wanted us to get rid of alpha. You know there's enough, we know all the skills now. We know how to do anything. If I want to get rid of alpha, and I know that this is in terms of this, I've got enough trig skills to be able to deal with all of that I've got there, okay? Were there any other ones from this paper that we wanted to talk about?
For this one,
Yeah.
the impulse always perpendicular to the thing.
Yes.
Yeah.
Yes, the impulse will always be perpendicular to the like
Direction.
to the direction of the collision. So like if you had two balls that were colliding like this and like this, they're going to hit each other in the middle. So the impulse is going to be like this and like this.
Can we look at 4?
And then we'll look at 4 as well. Okay. So still sticking on a collisions theme.
Your explanation was so
This is the easiest 13 marks of my life.
For question 4.
The last question then. The two walls. Two walls questions are probably going to be my favourite.
I'm hoping you've all remembered for the two walls questions those vector formulae that we've had. Because if you use those vector formulae, everything is so easy.
You just one step over.
It's just, everything is so simple. You just have to memorize those formulae, okay? Okay, well I can just shrink this a bit. I'm just going to put that over the top. Okay, so another collisions one we've got here. Two small smooth spheres, A and B, masses 3m and m respectively in equal radii. The spheres are moving on a smooth horizontal surface. Sphere A has this velocity, sphere B has this velocity. When the spheres collide, their line of centres is parallel to J, as shown in figure 1. That whole paragraph at the top is just figure 1. The coefficient is E. The kinetic energy of B is the kinetic energy of sphere B immediately after the collision is 85% of its energy immediately before the collision. Find the velocity of each sphere immediately after the collision and then the value of E. Okay, so I'm going to draw out my diagram again. I've got these two things like this. This one is coming along 5 along and 2 down. And I've put the 5 here because it's not going to change, is it? And then this one is coming 3 along and 4 up. So I'm going to put the 3 along because it's not going to change. And then you've got the 4 up that's here. This has a mass of 3m. This has a mass of m. After the collision, I don't know which direction they're going to be moving in, but which directions did you put them in? Did you just do them both going down or both going up?
Up.
You did them both going up. Probably better to do that, actually. And did you call them x and y?
Yeah.
Okay, good. So we'll call this one x and this one y. So all we're actually being asked to do here is to find out x and y, okay? What are the steps that we need to do to be able to do this?
PCLM, then MLR.
Okay, so let's do PCLM.
So it's
We'll take upwards as the positive direction, I think.
okay,
So we get 4m minus 6m equals 3mx plus my. So that's minus 2 equals 3x plus y. And then NLR is the speed of E is equal to the speed of separation, which is
1 minus x.
X minus y.
x minus y.
Oh, x has to be far, yeah.
Because in that scenario we're saying that x has got to be bigger. So the speed of separation over the speed of approach, which is 6. So we get 6e equals x minus y. And then we might actually need to use the other bit of the question as well, this 85%, but we'll come to that in just a second. So using these simultaneously, looks like what's going to be the easiest thing to do simultaneously?
Make one the subject.
Yeah, we could just add them together. That's going to be even quicker. So we get 6e minus 2 equals 4x. So x is equal to 3 over 2e minus a half. And then y would be equal to minus 2 minus 3x. So that's minus 2 minus 9 over 2e plus 3 over 2, which is minus a half minus 9 over 2e. So we've got those.
Do we even need to use uniform restitution? Because I didn't.
No, probably not.
Use the kinetic energy.
Yeah, probably. You're probably right. You can probably just go straight in with kinetic energy. I'm just in the habit of doing everything, and I know what I've done there is probably going to help me with part B, I should imagine.
Sort of. Just like a one line for part B.
Well, you do need to do NLR at some point, though.
Yeah, right at the end.
So at this stage that we've got now, if we want to say that the kinetic energy has been lost. The kinetic energy of sphere B is 85% after as it is before. So which one's B? This one down here.
Mm.
So that must mean that a half y squared
Yeah.
is 85% of a half m times 4 squared. So yeah, you're right, we probably didn't need to do this at all. We
So
just,
you have to use total
Yeah,
speed.
you have to use the 5 and the 3 as well, don't you?
Yeah. 4, 3.
you do, but I don't actually know if it's going to make much of a difference, but you're
Yeah,
right.
Because the 3 is constant. So half m3 squared is going to be on both
You're
sides.
using the speed. This you're using the speed, not you're using the velocity.
So you get a half my squared
Plus 3 squared.
plus 3 squared is equal to 85% of a half
Oh,
m.
4 squared plus 3 squared.
Yeah, I do see what you're saying. 4 squared plus 3 squared. Yeah, that's right. Sorry about that. So the m's cancel. So you get y squared plus 9 is equal to 0.85 times 5. So y squared is equal to whatever that is. Have you got that, Luke? That doesn't. That's not going to work, though, is it?
25.
Yeah, so y squared.
Oh, y squared.
25, no?
Yeah, that's what I got.
Oh, 25.
Yeah.
Sorry. So what is y squared equal to?
Y squared is 49 over 4.
49 over 4.
So y is 7 over 2.
So y is 7 over 2. And then I guess we've already done all of this work over here. So we can now use this thing to find out what x is. Yeah, I suppose we didn't need to do that at all. So if y is 7 over 2, we can now use this statement to say minus 2 minus 7 over 2 divided by 3 is equal to x, which is
Minus 3 over 2 minus a half.
minus a half. So x is minus a half. And now actually we can go straight in if we wanted to with this statement that we've got over here for part B. So we've got the velocity, actually we haven't finished the question. Find the velocity of each sphere after the collision. So we should say A has a velocity of 5I minus a half j, and B has the velocity of 3I plus 7 over 2.
Isn't y minus 7 over 2? Because
Yeah, that's what I was
then both of
thinking.
them are we have to have both of them going down.
Yeah. That actually wouldn't make any sense there, but
Yeah.
because we had to take this square root part, then is that not going to
We
change?
take the negative value of 7 over 2, no?
Yeah.
Yeah,
And then we have to change it.
So this one has to be negative 7 over 2,
Yeah. Otherwise it doesn't make sense.
which means this
Yeah.
becomes a plus,
Yeah, and then x is going away from it. Yeah.
which then gives you that you have a half 7 over 2.
3 over 2, so it's just positive a half.
So x is a half. Yeah, that works. The other way around didn't work, did it? So I was just about to check that with this
I
bit.
wanted them as going opposite ways, so that's why.
That's why, because you just knew. Okay, so you got 5I plus a half j and 3I minus 7 over 2j. Yeah? And then the last stage is just to find out the value of E, which we can use this NLR bit that we've got here. So we know that E is going to be equal to x minus y over 6, which is a half minus 7 over 2 over 6, which is 4 over 6, or 2 over 3.
Yeah.
Yeah? Yeah, I guess with this bit you've got to be careful because you're square rooting, so you know that there could be a positive and a negative. You just need to look back at the context of the question and decide which one fits and stuff, okay? I think, yeah, there's so many ways you can do this question. So many ways. Okay, I'm going to stop there.